You guys ready for next week? Yes? So, huh? So on the test next week, we're going to use Scantron.
No.
No?
No.
Why? I'll provide the Scantron.
Okay.
Okay?
That's better.
Okay. I'll provide. How much will they cost?
Like 95 cents.
95 cents for a sheet?
You get a packet of 6 for you
Yeah.
get a packet of 6 for like $2 and some odd cents.
That's still a high profit margin. All right, so I'm going to provide the Scantron sheet. Now, that means when we start talking about the 3 problems, right? I'm going to give you multiple choice answers for the 3 problems. Okay? So that might help you out some. However, we're also going to look at them. Right? So if you got it right by guessing, but didn't have down the work that got you there, you're not getting credit. You might get partial credit for what you did, but you can't just guess, right? If you got it wrong, we're going to look to see what you did do for partial credit, right? So it's not just a right, wrong. We're still looking for partial credit on everything. So that you don't have to worry about, oh, I missed that one, that means I got 0, right? You still show me work, and that will get you credit. Even if you get the right answer and you knew how to get it, you need to show me some work, right? The one exception to that is there's going to be one problem that's going to look something like this. F equals 6.67 times 10 to the minus 11 times 5 times 10 to the 28 kilograms times 3 times 10 to the 26 kilograms divided by 3 times 10 to the 6 squared, and I'm going to ask you to calculate that, right? I'm not going to expect to see any work, because all the work you're going to do should be in your calculator, but I'm going to expect you to just calculate that. So that if you know how to use your calculator, and it won't be these exact numbers, it'll be something similar to this, but if you know how to use your calculator, that one should be a gimme, right? All right. If I've asked you to come talk with me about your exam and you haven't yet, please do that. Please do that. Okay, Eureka.
Here.
Michaela. Friend. Laurel.
Here.
Carly.
Here.
Kelly.
Here.
Joe. Here. Dakota. Here. Anna.
Here.
Carrie. Robert.
Here.
Diamond.
Here.
Marjwan. Dylan.
Yeah.
Tanisha.
Here.
Maisie.
Here.
Anna.
Here.
Justin.
Yeah.
Emily.
Here.
Caitlin.
Here.
Chelsea.
Here.
Bailey.
Here.
Bernicia.
Here.
And Shelby.
Here.
Colton.
Here.
Tony.
Here.
Colin.
Here.
Stacy.
Here.
Brian.
Here.
Chandretta. Stormy. Samantha.
Here.
Casey.
Here.
Rolanda.
Here.
Sheldon.
Here.
Marquavius.
Here.
James. Okay, so on the homework for chapters 10 and 11, you guys see that? Is it getting bright enough? So on the homework for chapters 10 and 11, I've tried to help you out by giving you equations and constants you need to work with. Right? You still have to look up things on some of the problems, but more of it is in the problem description. So hopefully that will help you in terms of understanding what's going on there. And now, okay. The outer planets are what? What are the outer planets? The gas giants. They are Jupiter, Saturn, Uranus, Neptune, right? They're basically 5 AU, 10 AU, 20 AU, and 30 AU out, right? So they're much farther out. Jupiter's more than 5 times away from the sun than we are. Right, we're at 1 AU, Jupiter's at 5.2, I think. Saturn's out at 10, Uranus at 20, and then Neptune out at 30. So they're all out beyond Mars, they're all out beyond the asteroid belt. They're gassy, liquid hydrogen, methane, things like that. The dwarf planets are out there too. But we call them dwarf planets because they are, smaller than inner rocky planets, and they haven't cleared out their environment. And then Eris is just kind of weird. All right, so Jupiter. You guys have seen Jupiter a lot, you just didn't know you were looking at it, right? Jupiter is one of the brighter stars in the sky. So when you look at it, you're not really seeing a star, you're seeing Jupiter. It's big, more than 10 times our diameter, more than 300 times our mass. It's all gas and everything, so it's got all these cloud structures around it. And let's keep meaning to... Okay, this is an image of the Earth. When we think about those bands of clouds around Jupiter, and we think that's kind of weird, why does it have that? But if you ever get accustomed to looking at pictures of the Earth, this is a picture of the Earth in infrared from just a few hours ago, right? So this isn't all that long ago. It was taken today at 1440 Zulu. Which would be, probably around 8 this morning, right? And you can see there's a line of clouds here. Now, because it is hurricane season in our half of the hemisphere, the clouds are up here just above the equator. And if you are a fan of looking at pictures of the Earth and you pay attention over time, this band of clouds will drift down to the other side of the equator when it's hurricane season in the southern half of the Earth. So we have our own band of clouds. All right. And if you watch, you can watch a storm come off of the coast of Africa, get really heated up over the Sahara, an air mass get really heated up over the Sahara, come off and form a hurricane, then come across. So it's pretty cool to actually watch the weather happen, which we have the technology to do now. So we, here on the Earth, we have our own cloud bands. Jupiter, because it's mostly gas, has lots of cloud bands. And they don't all flow at the same rate. The ones near the equator move faster than the ones further out. And then there's Jupiter's big red spot. What is Jupiter's big red spot?
Storm.
It's a storm. Right. It's an enormous hurricane. Clouds, water, ice, ammonia. There are other things there. We have organic compounds in the atmosphere of Jupiter. And then it rotates fast, right? Jupiter spins around fast. And because it spins around fast, it's equatorial. Because A, it spins around fast, and B, it's made out of gas. It has a bigger bulge at the equator than we do. So, what is Jupiter? Right. Gaseous hydrogen and then metallic hydrogen. You know, metallic hydrogen is something that on Earth is expensive to create because you have to keep it, one, very cold, down at a few millikelvin, right? And that's hard to do. Just a few thousandths of a degree above absolute zero, we can make metallic hydrogen. Jupiter has metallic hydrogen inside of it because of the intense pressure that it's under due to gravity. So that pressure causes the hydrogen to become metallic. And then at the very center, there's probably some iron, rock, and water. So average density is pretty light, 1.3 grams per cubic centimeter. Now, that's still, compared to water. Water is 1 gram per cubic centimeter, right? So on average, Jupiter is still denser than water, but that's still, in terms of planets, pretty light, are pretty, not very dense, let me put it that way. Cool thing about Jupiter, Jupiter actually emits more radiation than it absorbs from the sun. The Earth does not, Mars does not, Venus does not, Mercury does not, Uranus does not, Neptune does not, but Jupiter does. Saturn also does. And Jupiter and Saturn are our two largest planets in our solar system. And we believe the mechanism is the same one that drives similar to the one that drives the sun, in that the gravitational pull on all the gases in Jupiter causes an increase in pressure and an increase in temperature, and Jupiter radiates in the infrared. So Jupiter, you won't see it radiating, all you see is, bless you.
Thank you.
All you see is the light reflecting off of it. But if you could see in the infrared, you would see Jupiter glows a little bit. Right? Glows a little bit in the infrared. And I'm not positive. These dots right there, back in the 90s, the mid-90s, a comet hit Jupiter. Comet Shoemaker-Levy. And it made one pass by Jupiter and got captured by Jupiter's gravity and broke apart into a string of balls, about 7 different balls, and it went out and looped back around and then crashed into Jupiter. And it crashed into Jupiter, unfortunately for us, just out of sight on the other side. But we got to watch, remember Jupiter spins pretty fast, right? So we got to watch the places where it hit rotate around as Jupiter rotated. It was really, really cool. So, this is just to say, all that pressure causes the heat to build up, and convection brings it out to the surface, and so we get this infrared radiation coming out from Jupiter. You wouldn't want, so on Earth, so if we're in a hurricane, if we're in hurricane force winds, I could probably stand up on carpet and lean into the wind until it reached about 100 kilometers an hour. And past that point, the wind blows me away. All right? If you ever watch these weather reporters out there in the wind, you know, eventually they get to the point when they can no longer stand. And 60 miles per hour, about 100 kilometers an hour, is where we hit that point where the wind simply carries us off. On Jupiter, there's a jet stream on Jupiter because of how its atmospheric dynamics work that takes it up to 300 kilometers per hour. So those gases are zipping around pretty fast. We get all these belts going different directions, different speeds, and because of that, what was really cool when we got the Hubble up and we could take a good look at Jupiter, make a really clear picture, because of that, you've got a jet stream going this way and one going that way, and if you look at the boundary, there's all this swirling and going on and interaction between the two boundaries. And then, of course, the Great Red Spot has been there for a while. There was a, I'm trying to remember where it was. I think it was up here. There was a smaller red spot that formed and went away. It was there for a couple of years and then dissipated. Okay, so because Jupiter is made up of, we have a strong magnetic field because we have an iron core that's spinning. Jupiter has magnetic hydrogen spinning, metallic hydrogen spinning, right? So metallic hydrogen acts just like a metal, that's why it's called metallic, and that means it also has a strong magnetic field. Because it has a strong magnetic field, you know, a lot stronger than ours, 20,000 times stronger than ours, because it has a strong magnetic field. If you look in the right wavelengths, you can see Jupiter's version of the aurora borealis as particles from the sun, charged particles from the sun, come streaming in, and the magnetic field guides them to the poles. Also, because of its magnetic field, Jupiter has something akin to our ionosphere and Van Allen radiation belts, so that there is a region, around the Earth because of the magnetic field where we get this radiation flowing. Jupiter has the same thing. There's radiation flowing in a Van Allen belt around it. And of course, in this view, you get to see cool things like lightning storms on Jupiter. They have to be kind of somewhat dramatic. The other big surprise. This was a surprise when the Voyager probe went out. Jupiter has a ring system. Well, it was new. Saturn had a ring system because you can see that with a really good pair of binoculars. Jupiter's ring system we had not seen with earthbound telescopes. But when we got closer with the Voyager probe, we began to pick up the rings. They are much, as you would guess from the fact we haven't seen them before, right? We hadn't seen them before. They're much smaller than Saturn's ring, much thinner. Part of that is because, Jupiter being bigger is going to be more likely to pull things in than Saturn. And in fact, there's a process where some of the material in the rings in Jupiter gradually drifts in. Jupiter has moons. Jupiter has a lot of moons. So for size reference, this is our moon. This is Io. If you like sulfur, the smell of rotten eggs, if you like the smell of rotten eggs, you'd probably really love Io because it has sulfur volcanoes where it spews sulfur up. You don't look like you would enjoy that. Yeah. This, you can go watch a fictional movie about Europa. This is Europa. Have anybody seen the Europa Report? A not great sci-fi movie. So Europa, the surface of Europa is ice. But we now know that underneath that ice is a very large ocean. And so there in Europa, there is a very large body of water underneath the ice. And so one of the probes we want to send out next would be one to go to Europa and get down through the ice and sample some of the water. Ganymede. Ganymede, you can see, like our moon, Ganymede has these maria where at one point there must have been lava flow to the surface to give you a big flat plane. And you also see Ganymede is bigger than our moon. Io is actually a little bigger than our moon. Europa is a little smaller. And then there's Callisto. Callisto, all those bright spots on Callisto are from big chunks of ice hitting it. These four moons we'll sometimes call the Galilean moons. Why do you think we call them Galilean moons? Galileo saw them and discovered them. That's right. These are pictures of volcanoes erupting on Io. And it's really cool that we actually have a probe out there that managed to catch this happening, right? And one of the things we've learned in astronomy is if we happen to catch something happening, it's probably not rare, right? And so this is probably a process that's going on all the time on Io. Europa has no craters, or very few craters. Right? It's not like the others, and some of that is because Europa is mostly a shell of ice, and also because the tidal forces on Europa between Io and Jupiter keep things moving around. Europa continually reforms its surface. What we now believe is Europa is there's this layer of ice on top of everything. Right? Here's a nice picture. You can see, wow, that looks just like ice crystals, right? And then underneath, a metallic core, a rockier interior, and a metallic core. Right? So that Europa may have one of the largest oceans out there. So Ganymede and Callisto also have their own characteristics that have to do really with how far away from Jupiter they are. You know, the farther out from Jupiter you are, the more you're going to get whacked by stuff. The closer you are to Jupiter, the more tidal forces are going to do things to you. And so you can see they get whacked by stuff a lot. Again, one of those things you'll see we focus on all the time is there's ice. So water continues to be one of the most important elements, or one of the most important molecules we look for. And on average, these moons are fairly dense. And then the rest of Jupiter's moons are small. A lot of their moons. So the big moons and a bunch of the moons are all in the same plane orbiting around Jupiter, which would indicate that they formed with Jupiter. All right, just like the planets formed with the Sun, would indicate that these planets formed with Jupiter. But you go a little bit further out, and you've got moons going around Jupiter in all kinds of angles. All right? And these tend to be small, they tend to be irregular, and they are probably simply asteroids that came a little too close to Jupiter and got caught. All right? And so these asteroids, you know, we still... Right now we're up to, Jupiter has 63 moons, and we don't set that as, yeah, it's got 63 moons. It only has 63 that we've discovered so far, because it wasn't all that long ago when Jupiter had 12 moons, right? And we managed to get better and better at taking pictures and see more and more of these rocky bodies just orbiting around Jupiter. All right, so Saturn, remember Jupiter is 1.3 grams per cubic centimeter, a little bit more dense than water. Saturn is less dense than water at 0.7 grams per cubic centimeter. Diameter 10 times that of Earth, 95 times our mass. And these great big gorgeous rings. It has a lower enough temperature that we have ammonia gas that freezes into clouds. So the clouds of Saturn look a little different from the clouds of Jupiter because of what they're made up of. But Saturn also has these characteristic bands. Right? It has the bands like Jupiter, just not as turbulent. And again, heavy enough. We get more hydrogen, gaseous hydrogen, because Saturn is lighter. And then there's still a liquid metallic hydrogen and rock and iron in the very middle. And you know, this gives you a good size comparison. We can take Earth and stick it in the middle of Saturn to replace its iron core, right? So we have the main rings of Saturn that we used to divide into 3 big bands, but now that we've gone close and seen, there's actually an intricate set of lines, minor small rings that actually make up all of these. They span, you know, 30 kilometers to 136,000, 30,000 kilometers to 136,000 kilometers out. Here's a great picture. You can begin to see the fine detail in all of these rings. All right? All this fine detail. Now, one of the things we've discovered over time is that all of these rings and all of the little gaps in here, their position and their size is determined by some moon. In fact, there are some small moons in the rings themselves that are going around. And so the moons create a resonance in the gravitational pull between each other and the rings that the term we use is shepherd. They shepherd all these particles into that ring. So the moons are why we have the rings like we do. And the rings are probably debris from other objects that fell apart. One of the things that is interesting about the rings is you'll notice they kind of look different in color in this photo. Well, the way I think about it is kind of like different bugs coming in and splatting on the gravitational field of Saturn, right? The rings are different colors because they're made up of different materials, which probably means different objects came in and were torn apart by Saturn's gravitational field and formed different rings at different orbits. Right? So different objects over time, different objects have contributed to these rings. Some are icier, some are rockier. Here they're trying to illustrate the fact that we've got two moons that cause these rings to end up in the same place all the time. So basically what happens is, if you can imagine, all the objects in this ring are not moving perfectly together to stay in that one orbit together. They're drifting around, drifting out of that orbit. Well, every time they come through, these moons pull them back or push them back to where they're in that orbit that is the ring. And so as the particles that make up the ring try and drift out, the moons push them back. That's why we call them shepherds. And it's actually one of the ways, once we began to understand this process, one of the ways we began to find some of the harder to find moons was because we could see where the ring was being shepherded, and then we had to look and find, okay, I see all the sheep are staying lined up, where's the shepherd, right? One of the things important in forming rings is the Roche limit. Gravitationally, once you're within 2.44 planetary radii, right? Gravitationally, objects will not stay together, they'll break up. The tidal forces are too great for gravity to hold them together. Chemically, they can still hold together. So if you had a long molecular chain that was, 10 kilometers long for some reason, it could still hold together as long as it was chemical bonds holding together. But gravity will no longer hold stuff together and it'll break apart, which is why I think of these objects sort of splatting on Saturn's gravitational field. There is a point at which everything breaks up. And you can really see the Roche limit with Saturn and its rings and the rings of Jupiter, because the rings are all near that limit. All right, Saturn has a bunch of moons. Saturn has my favorite moon, actually. They tend to be smaller than Jupiter's. They tend to be denser, with an exception. So we've got Tethys, we've got Rhea, Dione, Enceladus, all of these. Here is Titan. The Titan is large enough. Titan gave rise to some of the sci-fi things that you saw, like in Star Wars, where they have people living on the moons of a giant gas giant. Titan has an atmosphere. Titan has oceans of liquid methane. Right? Titan, if Titan were not orbiting Saturn, we would be calling Titan a planet. Right? We would be calling it a planet if it were orbiting the sun. It's bigger than Mercury. It has an atmosphere. Right? It's got an atmosphere that's fairly dense. Right? Nitrogen atmosphere, methane oceans. All you need is a little oxygen and you can stay warm. when we look at the surface, this is a picture from the surface. This is a picture of the surface where you can see lakes. This is a picture where you can actually see sand dunes, something similar to sand dunes, right? And here you can see where there's a methane lake and there are rivers. Right? So Titan is the most, in a lot of ways, other than if you could breathe nitrogen and could swim in liquid methane, right? Titan in a lot of ways is the most Earth-like object in the solar system. And it's a moon of Saturn. So, visually, unless you really like this color, visually Uranus is one of the most boring of the gas giants. It does have rings. They're small, they're thin. It's out at about 20 AU or 19 AU. It's hard to study because it's so far away. But even when Voyager went by, right, it's pretty much featureless. It's just a big blue ball. No cloud structure, nothing like that, just a big blue ball. And it's blue because its atmosphere is mostly methane. Methane absorbs red. And what's left over is blue. A little heavier than water, right? 1.2 grams per cubic, a little denser than water, let me say it that way. A little denser than water, 1.2 grams per cubic centimeter. Not much rock or iron. Water, methane, ammonia. Equatorial bulge, right? That makes you think it's mostly gas and water on the inside. And then the odd bit about it. Oh, okay. The odd bit about it is its spin. So Uranus and Venus are the two oddballs with respect to their spin in the solar system. Because Venus is upside down from everybody else, and Uranus is on its side. Right? Uranus is on its side. So as it goes around the sun, it points in the same direction in the plane of its orbit all the time. Yeah. As we think about how could this happen, the only likely explanation that we can come up with is that it got hit by something pretty solid at one point. And all of its moons, right? All of its moons orbit not in the plane of the solar system, but around its equator, so it looks like they formed with it. Rings are dark, and just like with Saturn, we learned to begin looking for shepherd moons to explain the structure of the rings, but the rings are dark and they're thin, a lot of carbon, a lot of organic molecules. Then there's its one moon that, well, it has more than one moon. There's one moon that's pretty interesting, Miranda. Miranda is interesting in that if you look at Miranda, Miranda was very clearly struck and torn apart at some point, and the pieces came back together. As you can see on Miranda, where the boundary is, where it came back together, and these cliffs here, right, 12 miles high. These cliffs are 12 miles high, where two pieces just gravitationally got pulled back together. So, the last major gas giant, Neptune. Neptune, similar in size to Uranus, blue, but it has structure. It has its own storms, right? The great blue dot there, another smaller storm there. I say small because, I mean, here's the Earth, so this storm on the Earth is, you know, roughly the size of Mexico, but still small for Neptune. It was discovered because of irregularities in Uranus's orbit, right? So they'd see Uranus speed up, see Uranus slow down, and that was happening as Uranus came past Neptune in its orbit. So as Uranus approached Neptune, it would speed up a little bit, and as when it passed, it would slow down a little bit because of Neptune's gravity. And so astronomers began looking for another planet out there. Neptune's not easy to see, mostly because it's so far away, right? 30 AU, 30 times farther out from the sun than us. Similar instruction to Uranus, right? Molecular hydrogen, water, iron, a thin atmosphere. Methane in the atmosphere giving it its color. And deep interior heat source drives the convection currents. And it has very thin, delicate looking rings. Right? Just thin little rings. More dust. So Saturn and Uranus, their rings tend to be kind of rocky chunks. And Neptune's rings tend to be just dust. Whatever made them up really got pulverized. Triton is a fairly large moon for around Neptune, and a little different because it orbits backwards, right? So Triton is probably something that Neptune captured at some point and pulled into orbit. Has craters. And, you know, again, it feeds into having a little bit of an atmosphere. It has geysers. So one of the things that drives having an atmosphere for all of these for rocky planets is, are they volcanically active enough to replenish the atmosphere that escapes off into space? We lose atmosphere to space all the time. But we're volcanically active enough to replace that atmosphere. Triton also has some really, you know, it'd be nice to be able to study all of these planets, all these moons and planets up close for a long time, but we can't afford that yet, right? But interesting as we did our flyby with it, interesting structures here and there. This is volcanoes going off with the streaks of dust from the volcano. Okay, and that gets us through the outer planets. Any questions on them? No questions. 0 questions about the outer planet.
I have a question about homework.
Okay.
Okay, so we have lab today,
Yes.
and according to Canvas, chapter 10 and 11 are due the 20th, and then we have to do chapter 9, so we didn't do it last.
Right.
So is chapter 9 the one that's due tonight?
Yes. Yep. Other questions? Questions about homework, other than mechanical questions about when it's due? You want to look at number 4?
Yeah, that big thing.
look at number 4. Chapter 9, number 4.
Yep.
I mentioned earlier that if the nursing staff over at the Student Health Center just gave us a clicker, and I just clicked every time I had a sneeze in my class or a cough, they would have an early warning system for whether or not people were being either sick or not. Number 4. How many times brighter is sunlight at Venus's distance from the sun than at Earth? How many times dimmer is it at Mars than at Earth? Just sort of in the appendix, brightness is B.